Hi, this is Tzvi Rosen with another lecture on the history of calculus. In today's lecture, we'll talk about Johann Bernoulli. Just a quick biography of Johann Bernoulli to start. He was born in 1667 in Basel to the same illustrious Bernoulli family that we discussed in the last lecture. That makes him 12 years younger than his brother Jacob, so he was very much a younger brother. In university, he studied medicine while learning mathematics from his older brother Jacob. At that point, Jacob had returned from his studies abroad to the University of Basel and received his professorship there. After studying in university, he taught mathematics in Groningen and then took over Jacob's post in Basel after he died in 1705. Then Johann himself died many years later in 1748. Johann had a bit of a reputation for getting in spats with people. First of all, even though we mentioned he learned mathematics from his brother Jacob, he also developed an intense rivalry with him. In a letter that he wrote to L'Hôpital, he wrote that he finds it unbearable that I, the younger brother, receive as much esteem as he, the older one, does, and he would take great satisfaction in seeing me miserable and reduced to humility. Clearly, their relationship had gone sour, and for the last several years of Jacob's life, they were not on speaking terms. In another incident, Johann wrote a screed about a student who had slandered him, describing him as an utter ignoramus. He also argued with the clergy at his university, who wanted him to stop running medical experiments in the university chapel. He insisted that the study of medicine was a divine pursuit, and so they should just let him do it. A little bit more sinisterly, later in life, his son Daniel became an eminent physicist, and they both worked on hydrodynamics around the same time. But according to several historians, Johann wrote a date on his article about hydrodynamics, so that it would appear that he had written it earlier than his son Daniel, and in fact they had written it around the same. They had made the discoveries around the same time. So he was certainly a controversial fellow, but his mathematics is hard to dispute. The incredible contributions he made to mathematics. So one way he did this was by way of his student L'Hôpital. And L'Hôpital was a French nobleman, the Marquis de L'Hôpital. He paid Johann a salary for tutoring and for exclusive access to his lecture notes. Using these discoveries, he published the first calculus textbook in 1696. Everything previously published on this matter were research papers, and this was the first textbook. And it's a picture of the cover of, I don't know if that's the first edition, but a picture of the cover is in the side here. Analyse des infiniment petits. I'm sure that's horribly mispronounced. And really, most of the original stuff in this textbook comes from the research that he got from the results that he was sent by Johann. And he writes in the introduction, "Finally, I am greatly indebted to the Bernoullis, particularly the younger Bernoulli, who is at present a professor at Groningen. I have made free use of their work as well as that of Monsieur Leibniz. They may take the credit for as much of this work as they please, and I am quite content with what little they leave to me." So he never claims to be the creator of the material in his book, and yet we still call the famous L'Hôpital's rule by his name, and that was something that seriously irritated Johann after the fact. The statement of L'Hôpital's rule is as follows. First, we'll say it in its original language, though translated into English. Suppose y is expressed by a fraction, the numerator and denominator of which do each of them become 0 when x equals a. If the differential of the numerator be found, and that is divided by the differential of the denominator, after having made x equals a, we shall have the value. Okay, so that's very wordy. They didn't have the precise notation and concise notation that we have today. Writing it in modern notation, we have let y equals f of x over g of x, with f and g differentiable for x not equal to a. Then if f of a equals g of a equals 0, and the derivative of g is not 0 for x not equal to a, then the limit as x approaches a of f over g is equal to the limit of f prime over g prime. The spirit of L'Hopital's proof is as follows. If you have f of a plus dx divided by g of a plus dx, where dx is an infinitesimal which will be sent to 0. So the values of f and g near a can be expressed in terms of the derivative at a, okay, assuming that the derivative exists. So we have f of a plus f prime of a times dx, and g of a plus g prime of a dx. And now we know that f and g are both 0 at a, so this vanishes, and dx is going to cancel itself out. So we're left with f prime of a divided by g prime of a. So that's simple enough. Obviously, the details here are not rigorous because we're not using the precise language of limits, and we're assuming the derivative exists at x equals a. But that kind of precise machinery wasn't available to L'Hopital yet. That would wait till later. The formal language of limits would come with Cauchy. Okay, so that is the idea behind L'Hopital's proof of his rule. And now we can do an example. And this is an example that comes directly from his textbook, from L'Hopital's textbook. So we're going to compute the limit as x approaches a. So he didn't use that language, but this is the function that he was trying to compute the limit of a squared minus ax divided by a minus root ax. Okay, so first we check that both vanish when we plug in x equals a. So we know f of x equals a squared minus ax, and g of x equals a minus the square root of ax. Then it's not hard to see f of a is equal to a squared minus a squared, which is 0, and g of a is equal to a minus the square root of a squared, which is 0. Okay, so that condition is satisfied. Meanwhile, g of x, or f prime of x, and g prime of x are computed as follows. So f prime is minus a. That's just because a squared is constant, and minus ax has derivative minus a. And then g prime of x equals, now we have to use the power rule, minus root a times x to the 1/2. So we have minus root a times times the derivative of x to the 1/2 is 1/2 x to the minus 1/2, or 2 root x in the denominator here. So this is g prime of x. And so now we can compute the limit by plugging in x equals a. So the limit of our expression is going to be minus a divided by minus root a over 2 root a, and that equals positive 2a. Okay? So this is an application of L'Hopital's rule to a rational function, or I guess it's a rational algebraic function. When L'Hopital wrote his textbook, there were no The logarithmic functions and exponential functions were not widely understood, nor were trigonometric functions. So pretty much all his examples involved roots and polynomials. Okay, so that's an illustration of L'Hopital's rule, which really was discovered by Johann Bernoulli. And Johann Bernoulli did numerous other mathematical things. That he was considered a founder of the calculus of variations with his brother through his solutions to the brachistochrone problem and other topics. But he made some beautiful observations about this function, the function x to the x. And this is a study he made in 1697. And he was asking some basic questions about what is this curve, x to the x. Okay. So he started with what is the derivative of x to the x. From there, moved to what is the limit as you go towards 0. Okay, from this picture you can tell that it's going to be 1, but 0 to the 0 is really undefined, so it's not obvious why that should be. Then number 3, what is the length of the subtangent to the curve? And we'll describe what that means later. Where does x to the x achieve its minimal value? So this basin right here, what x value does that correspond to? And what is the area under the curve from 0 to 1? So if I want to take this area, what would that equal? Okay. So these are our questions, and we'll go through and present the answers that Johann Bernoulli was the first to produce. Okay, so we'll start with what is the derivative of this function? Well, we'll use this fact. Let it be given that when you take the differential associated to ln of x, you get dx over x. Okay, so using that, we start with y equals x to the x, and then we take a logarithm of both sides. Okay, applying the log rules, you get ln y equals x ln x. And then taking the differential, we get dy over y equals, now we have to apply the product rule. So we have dx, sorry, let's start with taking the differential first of the x terms, then it's ln x dx plus x times dx over x. Okay. And this gives us 1 plus ln x dx. Okay. So simplifying, or putting the dx with the other side and bringing the y over, we get dy dx equals y times 1 plus ln x. And subbing in what we know about y, that equals x to the x, this is x to the x times 1 plus ln x. Okay, great. So that's the derivative. What's the limit as x approaches 0 of x to the x? So the limit as x approaches 0 of x to the x, instead we're going to consider what is the limit of the log of this expression. So let's suppose that this is equal to L. We're going to take the log of both of these sides. We have ln of L equals the ln of this limit. And we can exchange the limit and the log. Again, the formalisms here were not known to Bernoulli, but we now know that this is permissible. And we can apply the log rules to say limit as x approaches 0 of x ln x. We can rewrite this in a form more amenable to L'Hopital's rule by taking ln x divided by 1 over x. Okay. Now, this is an application of the infinite form of L'Hopital's rule, which we did not prove earlier, but is still quite valid. And because both of these approach infinity as x approaches 0, we can take the derivative of 1 over x, of ln x, which is 1 over x, divided by minus 1 over x squared, which is the derivative of 1 over x. Okay? And simplifying, we obtain limit as x approaches 0 of minus x, which is obviously 0. If ln L equals 0, that means that L equals 1. So that tells me that the limit as x approaches 0 of x to the x equals L. And that is what we saw in the graph earlier. Okay, how about a subtangent? Well, first let's explain what that means. If we take a point on the curve, okay, so this is x, and this is the point x, x to the x. And then we draw a tangent line. Then the distance that we find between the intercept and the x value is called the subtangent. Okay, and we'll denote that by z for now. Okay, so how would we compute this? Well, we have two different ways to express the slope of the line L. Okay, so slope of L we know is given by the derivative, which we already computed, and that is x to the x times 1 plus ln x. And we know the slope of the line will also be given by rise over run, right? So the rise is x to the x, and the run is z. Okay, so setting these two things equal, we can solve for z. Okay, divide out by x to the x, and we obtain z equals 1 over 1 plus ln x. Cool. So that's the subtangent. How about the minimal value of x to the x? Right? What about this trough? Okay, well, students of calculus know that you find minima and maxima by finding where the derivative is 0. So if you set y equals x to the x, y prime, which is x to the x times 1 plus ln x, and you set that equal to 0, then we know obviously there are two choices. Either x to the x equals 0, or 1 plus ln x equals 0. Okay, so this first choice, x to the x equals 0, this is impossible. Okay, because no value of an exponential is going to be 0. As for 1 plus ln x equals 0, this means ln x equals minus 1, or x equals 1 over e. Okay, so that means that the lowest y value, the smallest y value of x to the x is 1 over e to the 1 over e. and this is approximately 0.6922. Cool. We should note that Bernoulli had not yet defined E in a way that was commonly used. So his finding the minimal value here was done using more approximation style techniques because he just didn't have the language to talk about what the solution of this equation is. Okay, finally, the coolest part, and this is the integral from 0 to 1 of x to the x dx. We'll start by stating a fact that can be derived by repeated integration by parts, that the integral from 0 to 1 of x to the n ln x to the nth power dx is equal to minus 1 to the n factorial divided by n plus 1 to the n plus 1 power. Okay, and we'll use that in a bit. Now, Johann Bernoulli didn't have an exponential function per se, but he did know that if ln of z equals y, then z could be written as 1 plus y squared over 2 plus y cubed over 3 factorial, etc. Okay, so he had this series expansion for the inverse to the logarithm function, even though he didn't have exponentials yet. Okay, so we know that ln of x to the x is equal to x ln x, and we're setting that equal to y. So that means in our case that z, so plugging in this z, which is x to the x, should be equal to 1 plus x ln x plus x ln x squared over 2 factorial, etc. Okay, so this is a kind of an evaluation of the exponential function where the variable that you're inputting is x ln x, and this should conform with our intuition that x to the x is equal to e to the x ln x. Okay, cool. So the next step is to use the fact, and this is playing a little bit fast and loose, and we'll see in the coming lectures that mathematicians started demanding more rigor with this type of argument. But Bernoulli assumed you can exchange the summation and the integration. So the integral from 0 to 1 of x to the x, which we have this series expansion for, 1 plus x ln x plus x ln x squared over 2 factorial, etc., should be equal to, and let's put a dx at the end here, should be equal to integral of 1 dx from 0 to 1 plus integral from 0 to 1 of x ln x dx plus etc. So you can integrate each term in the series. When you do that, you get the following. So we have x is the antiderivative of 1, evaluated from 0 to 1, plus, now this second term, that's where we're going to start applying this formula for the integral of x to the n ln x to the n. It's minus 1 to the n and factorial over n plus 1 to the n plus 1. So in this case, it's minus 1 to the 1 factorial over 2 to the 2. Let's write a few more terms before integrating. So we have plus 1 over 2 factorial integral of x squared ln x squared dx plus 1 over 3 factorial integral x cubed ln x cubed dx, etc. So continuing to integrate, so we have here it's going to be minus 1 over 2 to the 2. So here we have plus 1 over 2 factorial times minus 1 squared 2 factorial divided by 3 to the 3. And the next term will be 1 over 3 factorial times minus 1 to the 3, 3 factorial over 4 to the 4. And this continues. And what you notice is the beautiful cancellation of these factorials. So when we evaluate at the bounds here, we get 1 minus 1 over 2 squared plus 1 over 3 cubed minus 1 over 4 to the 4, etc. So this is equal to the sum of, from n equals 1 to infinity, of minus 1 to the n minus 1 divided by n to the n. Okay? This is quite an incredible sum. If we express it a little bit differently, then we would get this integral 0 to 1 of x to the x dx is equal to the sum of minus n to the minus n, where n goes from 1 to infinity, though we have to add a minus sign out here. So we get this incredible similarity between the term of between the integrand x to the x and the summand minus n to the minus n. So that it seems like something you would hope to be true but wouldn't possibly be true, that instead of integrating you could just sum something similar. And for that reason this is sometimes called the sophomore's dream. Okay. And I think that's where we'll stop our discussion of Johann Bernoulli's mathematics. We saw a bit of his life story, how he had some difficult conflicts with other people in his generation, but he was incredibly influential, helping the Marquis de l'Hôpital produce an influential calculus book, and producing beautiful mathematics like we saw his analysis of the curve y equals x to the x. Thank you so much.